will start. Thanks everyone for joining us today. It's my pleasure to welcome today's guest and to welcome you for the workshop on the use of AI in public spaces. It's my pleasure to welcome Dr. Yara Abu Awad, who will speak to us about fairness in algorithms. Dr. Abu Awad is a senior data scientist and group lead at Data Science Competence Center at the Swiss Federal Statistical Office. She supervises the team which implements data science projects within the Swiss public administration. Part of her work has been advising offices and educating the public about algorithmic equity and fairness. Dr. Abu Awad also participates in AI working groups at the United Nations. She completed her doctoral research in environmental health and epidemiology at Harvard Chan School of Public Health. Yara previously worked on a project with the Labor Office to evaluate whether an algorithm trained to match unemployed individuals to suitable jobs was discriminatory. She has also worked on evaluating whether or not machine learning can be used to predict poverty rates in Switzerland. And today, Dr. Abu Awad will speak to us about sources of bias in AI tools and dive into fairness, what it means, and how it can be measured with different mitigations methods such as Trusty AI and AI 360. I will be changing the slides. And yeah, thank you so much for being here. Please join me in welcoming Dr. Abu Awad.
Thank you. Thank you, Sophie. That was a really nice introduction. We're having some technical difficulties, so we're gonna bear with us as we try to sort of navigate moving through the slides. But I hope this presentation is not too long. I'm aiming for 45 minutes or 40 minutes. Just a question, how many people here have a background in computer science, or if you've ever trained a machine learning model? Okay, a number of you. So if I say things that you are not necessarily clear or you don't understand, have we decided if we want this to be interactive or not?
We can, yeah, I think.
So you can interrupt me. If you have a question, I'm sure somebody else also has that same question. But technologically, let's see what happens. So I guess we can start. Okay. Oh, the images are not appearing. Maybe if you click again.
Let's see.
Oh,
yes.
Okay, thank you. So I don't know if you've heard about the scandal in the Netherlands. I think the benefits office was trying to detect fraud cases. And so they built a machine learning algorithm. And so they were unfairly targeting people with lower income or who weren't of Dutch origin. And this has led to a lot of problems and quite a big scandal for the Dutch government. Sophie, you had told me that someone would talk about this at some point?
Briefly, yeah.
Briefly, okay. So I'm not going to get into the details of this, but algorithms are increasingly being used more and more in public spaces. Algorithm Watch recently published an infographic showing that a lot of cantons in Switzerland are using AI to process income tax declarations as well. So it's slowly creeping into government work as well. Yeah.
Yeah, I'll let you.
A lot of you have probably used generative AI. We see a lot of gender bias in the images that it generates. If I ask for a manager, I see a man. If I ask for a compassionate manager, I see a woman. You know, I'm more likely to see a woman. We also have gender bias in text. Again, this is just a translation website that uses AI for translation purposes. And so if this is in French, so if I say the doctor is happy, then it's immediately going to assume that the doctor is masculine. If I say the nurse is happy, it's going to use the SE, which indicates that the nurse is a woman, right, not a man. And for a secretary, it's also going to assume that it's a woman and not a man. Right? The other problem, of course, with generative AI is that it hallucinates. So there's a tool by OpenAI called Whisper that was used in medical settings by doctors to create patient notes. And it turns out it was inventing text, it was inventing sentences that the doctors had never even said. In the medical setting, AI is being increasingly used to process images and to help with diagnoses. This is a paper by Dr. Gassamy, her name isn't here, but this is a model that was trained just using X-rays. The patient's gender, age, their race was not entered into the model in any way. But it turns out that algorithms can identify your race, your sex, and your age using just an X-ray. And we'll talk about heuristic shortcuts a bit later. And so you can see here, we see underdiagnosis rates. And you can see that women are more likely to be underdiagnosed. In this data set, younger people are more likely to be underdiagnosed, Black and Hispanic people, and also people on Medicaid. If you don't know what Medicaid is, it's a type of insurance for people in the United States whose income is below a certain amount. So this is the poorer subsection of the population. And if we sort of dig into these groups a little more, we see that by intersection, so do you guys know what intersectionality is? It's when you have multiple, minority identities or underprivileged identities. And so if we break down the women, we also see that the effects are stronger if you're a woman and Black, et cetera, et cetera. So you might be wondering, what are the sources of bias here? And I'm not going to get into large language models because I feel like am I going to get into large language models? I don't remember my presentation. If I don't, and you're interested, just ask me later, but it's not really my area of expertise. So let's say if I start with a simple algorithm, and by the way, the term algorithm doesn't just apply to algorithms like machine learning algorithms. You can create a rule-based algorithm as well. This is a very simple formula that was used for a long time to predict the GFR, the glomerular, I can't say that word, filtration rate, which is your kidney function. And it was used to estimate it if, in place of a test, a more detailed test. And you can see here that if you're Black, you're automatically assumed to have a higher GFR. This caused a lot of controversy because using race as a correction factor is a simplistic distillation of ancestry and genomics, right? Like, what does it mean to be Black physiologically? It assumes that race would be a sufficient proxy for some of the observed differences without consideration of socioeconomic, dietary, or environmental factors. The downstream consequences vary by clinical context. So sometimes they're bad because somebody might not get a kidney transplant if their GFR is assumed to be higher than it actually is. And sometimes they're good, right? It depends on the context. This is a relatively simple algorithm, and now the guidelines have changed. This is no longer used, right? Black was removed as a proxy from this equation. The challenge with AI specifically, however, is that even a very small model, this is a small convolutional neural network, has 1 million parameters in it. And so it's harder to detect if there is bias. It needs to be evaluated differently. We're going to cover some of that. So how does bias get introduced into a model? Well, society itself is biased, right? And so that means our data is going to be biased. This is, sorry, it's in French. So Amazon had a recruitment tool that they created using AI. And they ended up having to scrap it because it turns out their recruitment tool didn't like women. Why? Because the data that they trained their tool on reflected their historical biases of hiring more men. And so the model just learned, well, if it's a man, then they're preferred to a woman. And we're going to talk a bit about that. This occurred even though the candidate's gender was excluded from the data. So you might be wondering, well, if their gender was removed from the data that was used to train the model, why is the model biased? Well, this is discrimination by proxy. So if a woman had gone to an all-women's college and this was in her CV, the algorithm would discriminate against her. If she had text in her CV saying like member of women's hockey team, then the algorithm would discriminate against her. So even if you remove the protected attribute, which signifies gender, the model can still discriminate by proxy. The other issue is whether or not the data is representative. There was a very big push a few years ago. I don't think it's still ongoing, maybe it is, where people like to use data from social media to do things like sentiment analysis. And so they would scrape the web, grab all the tweets on Twitter or X, and train an algorithm to predict certain things within a population. The problem is that the people who use these platforms are very different from the general population that you're interested in. They tend to skew younger. And so really, what are you trying to say? What are the conclusions that you're coming to from training an algorithm on this kind of data? There's also the lack of representativeness in the data. So if you're training an algorithm to detect skin conditions, if you only use white skin, then the algorithm is not going to work on darker skin tones, right? So your data is not representative of the underlying population. So can anyone tell me how this algorithm is making its predictions? So on top, we see the predicted value, so the value predicted by the algorithm. And on the bottom, we see the true value. So can anyone guess how this is happening? Yes? So the answer that I got was that it was a nature background. Is there another suggestion? Yeah. The snow specifically is the second suggestion. Yeah, so it's nature or snow, right? So a wolf is more likely to be photographed with snow in the background, right, compared to a husky. And so the algorithm was like, why am I looking at the dog? It's easier to predict with snow, so I'm just going to use snow as an indicator of whether this animal is a dog or a husky. This happens because in the data, as in real life, you're more likely to see a wolf in snow than you are a husky. Or maybe the photos used to train this algorithm, right, didn't have enough photos of wolves not with a snow background, right? So what was the data that you were putting into the model to train it? The other time that we see heuristic shortcuts, this is the same study where I showed you that women were more likely to be underdiagnosed and Black people. From that same research, what they did is that they took, it's a bit pixelated, sorry. They took the model that they used to predict the illness from the X-ray, and they froze the weights, and they used that same model to predict the protected attributes, just to see how much that already trained model could capture of age, sex, etc. This is the area under the curve. And it basically showed that the fairness gap gets bigger, the better the model is at predicting your sex or your race or your age. So it's using this shortcut to determine your diagnosis. They actually have a GitHub and all their code is online if anyone is interested in looking at this. Another example of a proxy variable, this is a paper where they were trying to predict pneumothorax, which is the presence of an air bubble in your chest. The treatment for that is to place a chest tube in your lungs. So the algorithm basically said, well, if the person has a chest tube, they have pneumothorax, right? But obviously you want them to learn from the lungs and not from the chest tube. In this particular case, the researchers annotated some pixels in the image and which partially solved the problem, but not fully. So if we think about bias that can happen in sort of different stages of training a machine learning model, I'm going to say at the very end, it says inference. People sometimes make the mistake of making causal inferences from models that were built to make predictions. These are not models that are built for causal inference, right? Causal inference, if we have time, I put a lot of slides in here. Causal inference requires very specific assumptions. So please don't do that. But when you're gathering your data, you can have issues like sampling bias, confounding bias, labeling bias, right? Even if you think about practice within a medical setting, How often are women ignored? How many times are they given a diagnosis? Do they even make it into my data set? In the US, it turns out that people from underrepresented groups tend to have less high quality or lower resolution scans. They don't get to get the latest tech high quality scans that other people do. And then of course, feature bias, like the feature that I'm using in my predictions, is there like a systemic difference in quality in wealthy versus poor neighborhoods, for example? And how is that going to impact the model that I'm training? How am I optimizing my model? Okay, I'm going to say test and train sets and validation sets. Does that make sense to everyone? Is anyone completely lost? Do you want me to explain what those are? Yes? Briefly. So when you train a machine learning model, it's not like a regression where you sort of tell it which variables to use, right? You just throw all the variables in there. Well, you can be a little more careful, but and the model learns the patterns in the data, right? That's why the data that you use is very important. For example, ChatGPT was trained on a lot of texts, but that includes Reddit, where we know what language can be like on Reddit, right? And it's learning those patterns. What you do though, as a user, so you're not telling it what patterns to learn, but you are specifying the hyperparameters of that model, right? The structure of the model itself. And so in order to teach the model what the best hyperparameters are, you split your data, you take a training set, which you're going to train your model on. Then you have a test set. I always confuse test and validation. So you have a validation set, which you use to sort of optimize, and then you have a test set that you leave out to see how well your model does in the end. So typically you're splitting your data into 3 parts to help you choose your hyperparameters and check its performance. Have I completely lost anyone? You seem okay. All right. And so the splits that you make, if by chance, right, if you're making a random selection, your test set doesn't include a certain underrepresented group, just, by accident, then your performance metrics are not going to reflect how the model will behave in the real population, right? Similarly, if your training set is not representative of the population, then your model, the way it's optimized, is not going to reflect its performance in the population. So those things are important too. These are not really, I would say, hard categories. Like you can categorize things any way you want. These are just lists. So for example, we have selection and sampling bias. We've talked about non-representativeness, selection bias, systemic measurement errors, lack of balance in the data. When data is unbalanced, models usually result in good areas under the curve, so good predictive power for the majority class, but not generalized to the minority classes. Strategies to mitigate class imbalance can result in further alteration of the disease distribution of the minority classes, or the distribution of whatever my target variable is, my Y, the thing I'm trying to predict. This is important because minority class representation in the overall data set may be small, right? So if I want this model to perform well in a minority population, do I have enough of them in my data set to be able to do that? We have historical or societal bias, so patterns of discriminatory decision-making. And this is behavior that can be amplified by algorithms. Even labeling, when you're creating a label for example, to say this person has disease or this person doesn't have disease, if they're from a group that's less likely to be diagnosed, they're an underdiagnosed group, then the thing you're predicting is also wrong in your data, right? So if you have an X-ray of someone who really does have pneumonia, but the doctor decided that they don't have pneumonia, then that's a problem, right? Your model is not going to train as well. Poor selection of predictors may result in a loss of important information. And sometimes the way people choose predictors, not typically in a machine learning setting, but if most of your sample is of the majority group, and you check if predictors are important by looking at correlations, et cetera, and you decide to drop some of them, well, that correlation is going to be driven by the majority of the data, which is the majority group, right? So you might be dropping predictors that are important for your minority group and not including them in your analysis. And then the confounding bias. So do you guys know what confounding is? Yeah. Some of you. So it's the presence of and I'll show you a little diagram afterwards. It's a common cause of the predictor and the outcome that leads you to believe there's a correlation between the predictor and the outcome that doesn't exist, or even if it doesn't exist. And so it can force the model to learn an incorrect relationship, leading to wrong conclusions. So the example here, there was a data set of chest x-rays and people were trying to use it to predict whether or not the patient had COVID. And it turned out one of the hospitals that they got images from was a COVID specialist hospital. And so the model was like, well, I just need to figure out what hospital that person was in, and I know whether or not they have COVID. Of course, the data source affects disease status, right? But also, it's being used by the model to predict COVID. Now, it can be inferred from patient positioning from the image, even if metadata is not supplied. So nobody on this X-ray data said, this is from hospital X and this is from hospital Y. The algorithm figured out that these X-rays are all the same, right? If you think about an X-ray machine in a hospital, the patient is in this many centimeters from the edge of the image. In another hospital, they're like this many centimeters. So the algorithm could discriminate between the sources of these X-rays and created this shortcut without being told which hospital they actually came from. And of course, the solution here to mitigating this bias is to just use data from the same hospital. Right? So the model wouldn't learn. These researchers tried doing a lot of things. They cropped the images, nothing worked. So their conclusion was you need data from the same hospital. So during modeling, I told you earlier about the choice of train or test validation splits. These have to be representative. A loss function is used to optimize my parameters so that I can predict the thing I'm interested in, right? And so if you choose a loss function on the basis of the overall model performance rather than for each subgroup, this skews the performance of the model to the majority group. So it's going to be predicting very well in my majority, but not so well in my minority groups. And then user behavior post-deployment. If the model is retrained using user behavior after deployment, this can amplify bias. So it just gets worse. This is kind of repeating what I showed earlier, but just showing that it can happen in many different, and this thing about influencing the context, I saw the recording of the talk about gender and online dating. I was listening to a podcast by a computer scientist who was actually saying that AI is impacting our evolution because people are meeting on dating sites and having kids. So that algorithm is actually like influencing the genetics of our species, which is kind of creepy, but anyway. Before I get into explainability, so knowing how common bias is means that models should be evaluated for it prior to deployment. This is something I believe. So, but first, a small tangent on explainability. Before my tangent, does anyone have any questions? Yes.
Important to select loss function for each subgroup, plus performance for community groups or side groups. But anyways, how do you go about selecting some? How do you go about finding it? So that's,
How do I find this? Oh, how do I find the subgroups?
Yeah.
Oh, how do I define them? Oh, I see. How do I identify where the model, for which groups the model is not performing very well? Well, typically the way we do it is we think about groups within a population that we think are being discriminated against, and that's how we pick, I haven't thought specifically about that problem. I have to think about it a little bit. If I don't know what the subgroups are, right? I can look at how well the model performs in different, with respect to different categorical variables within my data, and maybe that'll help me, identify which subgroups it could be underperforming for. So I would pick different categories and see like urban versus rural populations, people living in spatially, right? If I'm predicting something spatially, is it performing as well in Ticino as everywhere else in Switzerland? Yeah, so you could look at different categorical variables and see how well the model performs. Well, I'm going to talk to you about that. Hold it. Hold that thought. Any other questions? I don't have a perfect answer, by the way. Like, I know. So we don't really have a lot of time to talk about explainability. I think it's generally acknowledged that most models are a black box. A lot of people disagree with this. They get mad when you say this. You can disagree with me, okay? This is my personal opinion. We can use certain methods like counterfactual explainability. I'm going to talk to you a little bit about counterfactuals later if we have time. But this question can be posed. What would have to be different for this individual to have a risk score of 0.5? And we can say to the patient, so this is an algorithm to give you a risk score for diabetes or something. So if your plasma glucose concentration is 158.3 and your 2-hour serum insulin level is 160.5, you would have a score of 0.51. So it's explaining to you how the model came up with that score for you. A lot of my examples are medical because I have a background in epidemiology, so there's a bias there, but you know, I'm sure you can like transpose this to other problems. So most explainability is post hoc. So after you've built your model, right, you try to explain what it did. You can see, you know, how sensitive is my model to these different variables. You can calculate variable importance. That's usually easy to do in whatever coding language you're training your model. And you can see whether certain design choices, what impact they had on maybe like the spatial distribution of your predictions, et cetera. Depending on the size of the model, this can be very time consuming and may require a lot of time to compute. One of the first papers that I published was on using support vector machines to predict air pollution. And I was submitting to a journal where I think the reviewers just weren't very familiar with machine learning. And they made me do this. They made me fit the model like a million times without every single variable. So it can be very time consuming. There are standard solutions like Lime, but they have their limitations. I mean, they have their benefits, but they also have their limitations. And algorithms can be used to explain other algorithms. So, you know, people are now assessing the bias of LLMs by using other LLMs. You know, if we're going to end up with an ecosystem where AI is checking on AI, and that's great. And so, for example, I'm going to show you a method called PackMap. I should have written what it stands for because I've forgotten, but you can look it up. And it was used to generate this diagram, showing the two-dimensional projection of the concept space in a transformer model. A transformer model is the model used to create ChatGPT, for example. It's very good at predicting sequences. So it's used for, you know, like predicting gene sequences. It's also used for language because it's like, well, conditional on all of these other words, what's the next word going to be, right? And so it works in that way. This is from a very cool paper where what they did was that they took data from Denmark on adults, and they had their health data and their employment data and something else, their income data. They created their own special language to encode life events, and then they used a transformer model to predict whether people were going to die or not in their 30s, which is actually really hard to predict. And that's why they picked that specific problem, and to predict certain personality traits. And this is terrifying, but they actually did it. It actually works pretty well. They do have a very rich data set. You know, Denmark happens to be a place where data is stored centrally, like it's very socialized medicine, et cetera. So this sort of richness of data is probably not available everywhere. But so by encoding life events and creating their own language, they were able to build a transformer model that does this. And they generated this sort of two-dimensional image to show how these concepts were represented. And you can see that the model, for example, put all birth years next to each other, right? They have, you know, all maternal, like related health issues in one section by themselves. The authors said that in terms of health, the representations mirrored ICD-10 codes. Are you familiar with ICD-10 codes? Some of you are. They're codes used by hospitals for billing purposes, and they're kind of an international standard. And every time the ICD gets updated, everyone panics because they have to like recode everything. But anyway, you know, and so they were able to do this check and make sure that the language that they created, the model learned how to represent it conceptually in a way that made sense, right? So you can do this. I don't know if you can do this with an LLM like ChatGPT, which has like billions and billions of parameters, but if you have a small transformer model, you can probably do this. And PacMap is not the only algorithm you can use to generate an image like this. There are a couple of different ones. So some notes on explainability. Beware of claims over-promising to fully explain a model. There's a paper about this that I forgot to cite. And then if your explanation claims that a prediction was made due to a variable that is not it should say protected attribute and not predicted, sorry. This does not mean that your model is unbiased. So lack of proof of bias is not proof of lack of bias. Okay. Okay, so then we talk about fairness, but what type of fairness am I trying to achieve? I really like this table because it sort of summarizes the different types of fairness. We have group fairness measures, individual fairness, and causality-based fairness. What we've mostly been talking about so far is error parity, which is the model just as good in all of my groups, right? Does it perform as well for men as it does for women, etc.? Does it perform as well for rich people as poor people? And so typically this is what we care about if we're trying to predict, you know, disease in a population, or if we're trying to predict if someone is going to commit a crime, right? If the model performs really poorly in a minority population, and that person is more likely to be falsely accused of committing a crime, like in the Dutch case, this is a problem, right? So what can we do to improve error parity? And this goes back to the question I was asked about optimizing the algorithm. So there are a few approaches. So you can reweight the samples based on their group to combat underrepresentation. So, you know, if women only make up 20% of my data set, I can reweight them to make up 50% of my data set. You can adversarially remove group information from model representations, or you can generically attempt to improve model generalization, that is to use an exponential moving average. And so this is that same paper that I'm showing you things from that I cited earlier. Oh, the citation is there. And so what am I seeing here? So vanilla ERM is just a model with like a classic loss function, right? I'm optimizing just to reduce the error overall in my model. Subgroup robustness, this is where they reweighted the sample. Group adversarial, you're removing information from the model. And then the general robustness, which is the moving average, is the one in pink. And it seems that subgroup robustness is the way to go here, right? Okay, let me take a step back. So my x-axis is the performance of the model. It's the overall area under the curve. So as I move to the right, the model performs better. The fairness gap shows me what is the difference in my model's performance in the privileged group versus the underprivileged group. So the higher up I go, the more biased my model is, right? And so I'm trying to find a compromise between performance and fairness. And so this seems to be the sweet spot right here. Does that make sense to everyone? Yes. I should note, there's a professor at Oxford of law who argues that, I should have put her name here, reducing the performance of the model for certain subgroups to make everyone equal may not be ethical. So if I'm using one of these optimization techniques, and now the model performs better for women, but it also performs worse for men, is that ethical, right? So anyway, no comment. So the drawbacks of these locally optimized models are models do not perform as well with regards to other metrics. So they're going to, for example, the F1 score or accuracy is going to be reduced. Is it F1 score or accuracy? I don't know. And then models are not guaranteed to be fair in other data sets. And so what this is showing is that, so this is the model on the original data, the data it was trained on. And when predictions were made on another data set, the model was still Pareto optimal, but it did not perform as well. So it looks like these things don't generalize. Okay. So if I go back to the table, so we just talked about error parity. Now I'm going to talk to you about demographic parity. So demographic parity is more of a concern when we are giving people opportunities. For example, admissions to a college program, somebody getting a job. This is also known as statistical parity and group fairness. So if 35% of white applicants to graduate school are admitted, demographic parity would be satisfied only if 35% of Black applicants were also admitted. So you're basically saying that your recommendation of someone or your choice of someone is independent of their protected attributes. And you can imagine this is, very easy to do, right? You train your algorithm, you take the top, 35% white applicants, the top 35% Black applicants, and you admit them into your program, right? I'm oversimplifying. That's not exactly, but you know what I'm saying. So you can check if your model achieves demographic parity. And so this is just a visual representation, right? These are your rejected candidates and these are your accepted candidates. And you can see that the ratios are the same of the minority group to the major group are the same, right? One criticism of demographic parity is that favoring a group to achieve equality in a specific case can inadvertently amplify the bias. For example, in job recruiting, increasing the acceptance rate for a group with relatively low skill levels may perpetuate the perception of poor performance, making fairness a complex dynamic issue. So what people are basically saying is that if you want to achieve this, you might admit people who are less qualified from the minority group. And so it makes people's perception of that minority group worse. This is typically the argument that people make against affirmative action in the US, for example. This argument is, assuming that all decisions are merit-based and et cetera. But it is an argument that people make against demographic parity. So the choice of fairness metric, I think, is a really political one, and it depends on the society. I've had discussions with a lawyer about this, actually. So it depends on the sort of the legal environment that you're in. What does the law say about discrimination, right? And how do you translate that into a fairness metric? Conditional demographic parity, for example, there's a paper that I'm going to cite. Nope. Oh no, I do cite it here. So they argue that this metric aligns with the EU court's gold standard. What does conditional demographic parity is? It's saying the same thing as demographic parity, that the decision to choose someone is independent of whether they're a man or a woman or Black or whatever, but conditional on certain attributes that they label are. So conditional on their education, for example, their experience, their skills. If I'm picking people for a job, like I want someone who can code in Python, I want them to speak English. So what are the rates of hiring people? Conditional on all of these attributes that I think are important. You have to be careful when you choose these skills. Are they also reflecting biases? And if you condition on enough of these R's, this becomes an individual fairness metric, right? Then we have individual fairness. There are two different approaches to achieving individual fairness. We have fairness through unawareness. So you do what Amazon did, right? You remove the gender variable and you train your model. Or fairness through awareness, which is similar persons receive similar predictions independently of their protected attributes. As we saw with Amazon, the simple exclusion of sensitive attributes is generally not sufficient to ensure fairness. So fairness through unawareness is not recommended. It's not easy to prove that a model is individually fair. It's not like demographic parity where you just count the ratios, or conditional demographic parity where you just estimate the ratios. So this is from the work of Cynthia Dvork. I don't know if you guys have heard of differential privacy. She's can I call her the mother of differential privacy? She was a computer scientist. She also wrote a paper about individual fairness, and she argues that if you can't achieve both demographic or both group fairness and individual fairness, if people within those groups are sufficiently are different from each other. And so, for example, here we have two groups, S and T. If this line represents my criterion to choose people, because S and T have different ratios of G0 to G1, then I'm going to admit more people from group S than group T, or the ratio, right? A higher percentage of group S than group T. So she sort of argues that you can't have both. Oh my God, I've been talking for 41 minutes. Should we stop here? Okay. Is everyone good so far? No? So then the last sort of type of fairness is causality-based fairness. So what is causal inference? The identification and estimation of causal effects. The book that I cite here is actually free online. You can download it if you're interested in causal inference. It was written by two Harvard professors. And so what we're trying to do is say, what is the effect of A on Y? And this can be represented by a directed acyclic graph, which if you remember earlier, I talked to you about confounding. That's what that was, you know, time is moving from left to right. I have my predictor here, or my causal effect, and my outcome, the thing that I'm interested in studying. We do causal inference by estimating counterfactuals. Counterfactuals answer the question, what if? And so are you guys old enough to know what this is? Yes. So, you know, the gold standard for evidence right now is a randomized control trial, right? You run an experiment, you compare what happened in the treatment group to the control group, and you say, I have evidence. And we know because of random chance that might not be the truth. And so we like meta-analyses, right? We like for a lot of people to do these studies, and then we pull the results together and see what's happening. There are many situations where we can't run a randomized clinical trial, either because it's unethical, the thing we're interested in kills people, right? Like I could give half of my population arsenic or not, nobody would approve that. Or it's hard to study because people don't tend to stick to diets for a long time, right? If you're interested in the effect of, you know, I don't know, not eating potatoes for 10 years, very few people are going to comply with your protocol. And so in the absence of being able to do a randomized control trial, you kind of have to use observational data, making very strong assumptions to say, what would have happened if this person hadn't eaten fries every day for 10 years, right? That randomized experiment doesn't exist. I could go back in time. That would be perfect, right? I'd go back in time, and every time that person tried to eat fries, I would like slap them out of their hand for 10 years. And then I would see their health outcome at the end of 10 years compared to them eating fries every day. That's not possible. So we do it from observational data. We don't have time to get into identifiability conditions, but they're very strong conditions. So the counterfactual fairness condition is that a person would have received the same decision if they had different values for their protected attributes. So if this person had been a woman, they would have gotten the job versus a man, right? And then there's also path-specific counterfactual fairness. It's identical to counterfactual fairness, but keeping certain attributes fixed. Answers questions such as, would the prediction be different if the person were a woman? This is just one example of a directed acyclic graph, which is predicting how well someone does in their first year of law school. And so you could say, well, if I change this person's sex, would they do just as well? If I change their race, what if I keep their LSAT score fixed, right? So that's path-specific counterfactual fairness. Now, the causal-based fairness approach, it requires knowledge of the causal graph, right? So you have to know what this looks like. There are efforts now called causal discovery, where people are trying to use machine learning to build these graphs. It's kind of tricky because of sort of the rules that govern the associations between things along certain arrows. I don't think we're there yet, as far as I know. Identifiability conditions for estimating these counterfactuals must be met, and this will lead to a reduction in prediction accuracy. So just like we saw earlier, the different optimization methods led to lower prediction of the model. this will also lead, because you're taking out some of the explainability, right? You're taking out some of the things that explain that outcome. Here's a list of assessment tools. As I told Sophie, I haven't really tested them. I've read some of the references that they use. I know the Google What If tool, it calculates counterfactuals, but the methodology that they use, makes really strong assumptions, like things are independent from each other and stuff like that. So use with care. And I'm